There is a further interesting result from the previous calculation. From the property of the sine function, we know that the sine of 2 theta is equal to the sine of pi minus 2 theta. Okay. So it means that if you calculate the length of the projectile with the initial angle theta I, it will equal to the length of the projectile launched with the angle pi over 2 minus theta I. Okay. This is obvious from this equation, right? If the sine of 2 theta I is equal to the sine of pi minus 2 theta I. So it means that if we write this equation a little bit further as the sine of 2 of pi over 2 minus theta I. So it means that if you launch the projectile with the angle theta I and the angle pi over 2 minus theta I, you will get the same horizontal length. In this figure, you can see that the length for the initial angle 15 degree is equal to the 75 degree, because 75 is equal to the 90 degree minus by 15. Okay, so that is about the length, the horizontal length of the projectile. Now let's discuss the maximum vertical height. In this figure, the maximum vertical height is when the object moves to the point where the vertical velocity is equal to 0 at this point, and we call the height from the x-axis as h, and this is the vertical height of the projectile. We can easily calculate this, the value of h as follows. For the maximum height, of a projectile, you can see that if we go back to that figure again, you can see that when the object is at the maximum height, and if we draw the tangent line here, we will have this line, the horizontal line. Okay, this is a tangent line. Okay, and since this is the maximum point of this curve of the path of the object, so we must have the slope of this line, or which is the dy by dx at the position of the maximum height. We call this point on the x direction as xh. Okay, so we have that dy by dx at the point xh must equal to 0, because the slope of the tangent line is 0. So for the maximum height, we have that dy by dx at x equal to 0. But from the equation of y as a function of x, we have that d by dx of vxi vyi over vxi x minus half of g x square over vxi square is equal to 0. And when you perform the derivative, we have that vyi over vxi minus, this is x square. When you take dx by d by dx for this term, we have 2 in front of this term, and it will cancel with this half. So we have that it is a gx over vxi square. Okay, and this equal to 0. So we can solve for xh to get that xh is equal to the vxi times vyi over t. And you can see that this xh is equal to half of r, right? And this is what we should expect, because if we look at this figure again, you can see that from the symmetry, the point of the point xh of the maximum height must be equal to the half of the length of the projectile. Okay, so we can use the symmetry to estimate that xh should be at the middle, or should be equal to the half of r. Okay, and we also get that from our calculation. Okay. Now we will substitute this xh to the equation of y as a function of x. Okay, so we have that at x equal to xh, y is equal to h, and we have that h is equal to vyi over vxi times xh plus minus half of g xh square over vxi square, and we substitute the value of xh to this x. So we have that h is equal to the vyi square over g minus of half of the vyi square over g. So we have that h is equal to the vyi square over 2g. You can see that the value of h here is the maximum height of the object if we throw the object upward vertically, okay, and if the initial velocity of the object is equal to the vyi, okay, it means that if you have an object and you throw it vertically, the maximum height here is equal to h. If the initial velocity is equal to the vyi, and this is reasonable because, as we discussed before, we can separately consider the motion of the projectile as the motion in the y direction and in the x direction. So it means that the motion of the projectile in the y direction is similar to the motion of the object thrown upward with the initial velocity vyi.